Great. So welcome, everyone. This is our fifth, I believe, FHE.org meetup. For those of you who don't know it, FHE.org is basically just like a meetup, a community where we talk about homomorphic encryption and other secure computation techniques. We try to hold those meetups on a monthly basis, and all the videos and slides are then posted to the FHE.org website. Sorry for the very crude web design that we have on there right now. You know, there is nobody really working on that full time, but we are working on revamping the website and making it a little bit more clean. We're also working on doing something a little bit more structured. You know, now that we have over 1,000 people, actually 1,200 people in the meetup group, we'd like to do something a little bit more structured so that it's not as, as chaotic every time. So my name is Rand. I'm the CEO at Zama, where we work on homomorphic encryption. So from time to time, we also present. But today, we are actually not the ones presenting. We have the team at Google who are going to be talking about the work they did on transpiling from C++ to homomorphic encryption. I believe that you guys want people to take questions during the talk itself. Is that correct? Okay, great. So if you have any questions, you can either put them in the chat or you can unmute yourself and you can ask them directly. Please be respectful, however, of people speaking. So if you do unmute yourself, try to remute afterwards and, keep everything kind of clean. We had a couple of Zoom bombers a few times, and to be honest, it's really not, it's really, really annoying. We're going to have a longer Q&A session at the end as well. So don't worry about that. And we've got, I don't know how long you guys got, but I have 2 hours here on the calendar. So, we can take some time to do that. Perfect. Okay, so I'll let you guys take on and introduce yourself, and the floor is yours.
All right. Hey, everyone. I'm Shruthi from Google's privacy infrastructure team. With me is Rob from Google's hardware team. Today, we're here to talk about the FHE Transpiler that we recently open sourced. Thanks, Rand and the FHE.org team for this invite. A couple of things, as Rand mentioned, please ask questions in the chat box or feel free to unmute. I will pause in between if there are any specific questions on the slide, and we can cover more general questions and discussions after the presentation as well. So we're here to talk about FHE and the transpiler and where it could help in making FHE more practical. Anything mentioned about future directions and application is purely my own concoction and not at all reflects the long-term roadmap of Google. Anyhow, next. So the outline of the talk kind of goes this way. We start with FHE, why it's so awesome, a bit of history, of course, the learning with errors problem, because we can't really do a talk about FHE without LWE, right? We then talk about what are some of the practical challenges to a widespread adoption of FHE, some cryptographic and engineering challenges, why do we even need a transpiler, what it is, and Rob is going to go into a much more deeper dive into the transpiler design, the features, some cool demos, and end with some limitations and open questions and future directions for FHE and for transpilers in general. Next, so what is FHE? As you all know, FHE is fully homomorphic encryption, and it enables computation on encrypted data. What does it mean? Next, so in the present world, data is encrypted at the client, stays encrypted during transit, gets decrypted at the servers for some computations to be performed, and it's re-encrypted again by the server to be sent back to the client. So the data stays safe and encrypted in transit, but not at the server, assuming a trusted server model. With FHE, next, we can even encrypt the data at server. This provides strong privacy guarantees and can be useful in many avenues of the world. Privacy has moved visibly to the center of almost everything in the tech community. It touches every area of our life across many features, email, social media, and so many of the critical things we do, like medicine and finance. One example that I think illustrates the benefit of FHE is imagine uploading your genome sequence and being able to run analysis and get some useful insights. But then there's a concern, who else can see the results of that analysis? But with FHE, you can guarantee that only you can see the results of that computation. Only the owner of the data can decrypt the result. This is privacy by design. And machine learning in medicine is growing leaps and bounds in many things like tumor detection, cataract detection. The immediate next question that arises is privacy, and FHE can make a lot of headway there. And not just medical, right? Financial institutions can safely offload things like fraud detection analysis on their transaction data, and all without any concern about data breaches. So looking back at FHE history, FHE has been around in concept for a long time. Right about when I think around RSA time, where probably accidental that it's a partially homomorphic encryption system. Partially homomorphic encryption meaning you can do either addition or multiplication, but not both. And then came somewhat homomorphic encryption systems, where you could do some additions, one or two multiplications, but that's about it. The first real notion of a fully homomorphic encryption scheme was first proposed in Gentry's thesis, I believe in 2009, which theoretically proved that FHE is in fact possible. Then considered the holy grail of cryptography, but pretty unreachable because of the initial implementations, which were super slow. I believe it took 30 minutes to do a single multiplication. Anyhow, Gentry's scheme introduced the concept of what we call bootstrapping, which we'll cover a bit later, which can convert a somewhat homomorphic encryption into a fully homomorphic encryption scheme. Initially, these schemes were slow, and with lots of improvements and optimizations and introduction of many schemes, bootstrapping became faster and faster. And I think the latest is TFHE scheme, and even the complete, which has bootstrapping time of 0.01 seconds, almost 10 milliseconds. Anyhow, the other notable schemes here are BGB, BFV, and CKKS, and they are more on the arithmetic side, but more on that later. Next slide. So as all cryptographic schemes, the hard problem that most promising FHE schemes are based upon is the learning with errors problem. A side benefit of learning with errors problem is that it reduces to shortest vector problem in lattices, which is great because there is no known polynomial time quantum algorithm to solve the SVP, the shortest vector problem. So we can technically claim that these FHE schemes based on LWE are quantum resistant. I should add a caveat there that that is always active research, but as of today, these schemes are kind of quantum resistant. So what is LWE? It's a lot like, next slide, a lot like the problem of solving a system of linear equations. It can be easily done by Gaussian elimination. Basically, given the blue thing and the green thing, find the red thing. And it's easy. But when we add what we call noise, it becomes a hard problem. Next slide. So the search version of LWE introduces what we call noise. So given the blue thing and the green thing, it's hard to find the red thing because of the yellow thing. The yellow thing is small noise that is added strategically and which is usually some form of discrete Gaussian, but more on that later. So the search version is find this secret vector. And then there is the decision version. Next slide. So the decision version of LWE is given the blue thing and the green thing, can you distinguish and confirm is the green thing totally random, or is it a blue thing multiplied by a red by a secret and added and with some noise added to it? So these are toy problems, and for real world instances, in the next slide, the toy problem is what we see, a small one, but in the real world, the parameters will be much more huge. So in the order of like 750 and like more bits, and each different scheme uses different parameters, and that's selecting of parameters is a problem and is a big open question in itself. Anywho, so using FHE, using LWE, how are we encrypting the message? Next slide. So looking at LWE encryption, this question that comes to mind is, hey, we have this error. How do we encrypt a message? Next. Simple. Just hide the message in the noise. And bear in mind, this is, don't get too technical about it. Not all FHE schemes encrypt the message in the noise, and it's not a perfect analogy, but it kind of applies for most things. Anyway, so looking a little bit closer into FHE, into LWE encryption with FHE, keygen select some parameters N and Q and generate a secret vector. That's generating the secret key encryption. To encrypt next, we generate a random vector A, an error vector from some distribution, a small error vector, and then a message. Here the message space is T. Not important, it just says that the message can only be from 0 to T, and that becomes apparent later. So if you see the second line, B is A.S plus error plus message, and the ciphertext here is A comma B. Next slide. And you can see that in decryption, you can basically take MB and you have the secret key B minus A.S, and then you do mod T. Mod T basically removes the error, and you get the message back. This is one form of LWE encryption. There are many other schemes, but most of them kind of sort of fall in the realm of message, error, and decryption strategically remove the noise. So we know that LWE encryptions or FHE schemes are fully homomorphic. So computing them means that you can technically just look at the B vector and see that you can add two ciphertexts and the messages would get added. But at the same time, the error also gets added. Next slide. So you can see here that the message and error, as you do more and more multiplications, the message get added, but also does the error. With addition, it's not super high, but with multiplications, the error tends to get high very fast. And when you do enough computations or too many computations, the error becomes so high that it totally garbles the message. So at this point, the attack ciphertext is in limbo. Like decryption, you cannot decrypt back the message. So the point is to predict and track the noise and strategically reduce the noise, and how reduce the noise before the ciphertext gets corrupted. Next slide. So how do we do that? Bootstrapping. Bootstrapping homomorphically evaluates the decryption circuit to reduce noise. This is very computationally intensive. So ideally, we would want to try to avoid bootstrapping, but also there's a trade-off between, like, if bootstrapping is fast enough, then you could always try to choose your parameters so more computations can be allowed and do less of bootstrapping or less times of bootstrapping. Anyhow, so having all of this terminology kind of sort of in mind, let's look at what does FHE programming look like. So mostly if we want to look at FHE programming without thinking much about cryptography, I think can be divided into cryptography and engineering challenges. There's, I think the previous talk on FHE.org was about FHE compilers and FHE programming. And that's a great talk for a good summary. But anyhow, so there are cryptographic challenges and engineering challenges for FHE programming. And coming to the cryptographic challenges, as we've mentioned, knowing the circuit depth is important. Tracking noise is important. And sure, doing bootstrapping so that the ciphertext doesn't get corrupted is a challenge. And selecting the right set of parameters to allow the right number of computations and to allow the right message space All of these are cryptographic challenges. So for the purposes of this FHE Transpiler talk and the initial version, we try to not deal with these cryptographic challenges too much. So we don't do noise tracking. We do bootstrapping after every operation. And we use the default parameter set provided by the TFHE library that gives us binary encoding. So one ciphertext can only encode one message. So coming to the engineering challenges. Engineering challenges in FHE is different because once you start thinking about, hey, you're only working on encrypted data, the programming paradigm changes a little bit. There is no such thing as if-else condition. All if-else becomes a mux, basically. If the condition, you don't know what the condition evaluates to because the server doesn't have the actual data. So if the condition of the if is resolves to true, the thing in the if condition gets copied to the output. If it resolves the thing on the else condition just like goes 0 and doesn't get copied to the output. So there are no loops and jumps. There is no variable length loop because then the server would not know when to stop if the loop condition is based on an encrypted ciphertext. There is no conditional jumps based on the data. There are no branch and bound optimizations. Like pretty much all the graph optimizations that we have are out the window. We have to assume all graphs are fully connected. And the fourth one is kind of a cryptographic challenge as well as engineering challenge, using the right scheme for the right type of computations. For example, some schemes have approximate computations and lose some precisions. Those don't always work with things like string processing. They're okay with like arithmetic floating point. But anywho, so with all of these new programming paradigm challenges in mind, when we look at actually trying to develop an FHE applications, we kind of are at a point, well, throw away everything you have and write everything from scratch again. But hey, we are a privacy infrastructure team. We should be making it easy to incorporate privacy, not asking developers to re-implement everything from scratch. So that's why we came up with the idea of FHE Transpiler. And I want to pause here if there are any questions.
Actually, can I ask a question here? Yes, I'm Quan from Melbourne, Australia. So you mentioned that there's no if-else clause, but I think we can rewrite the if-else clause in an equation. Let's say if C, then B equal A, else B equals something else. So you can rewrite that as B equals C times A plus not C times something else. And yeah, you can evaluate it homomorphically.
Exactly. All of else conditions either need to be converted into CMUXs or what you just mentioned, like rewrite them in a way that like homomorphically it makes it sense to take the output of the data and put it somewhere.
Oh, okay. Thanks. That's some question.
Yeah, you're totally right though. Any other questions? Okay. So back to the talk then. Okay, FHE Transpiler. So what's a transpiler? A transpiler converts a high-level language into another high-level language. You must have seen like JavaScript to Java or JavaScript to C++ transpilers. So what is an FHE transpiler? FHE transpiler allows you to convert an existing code that works on plain text to something that works on ciphertext. And the initial version of transpiler makes use of TFHE library and a bunch of other existing tools. Let's look at them one by one. The first tool is TFHE library. And next, why did we even use TFHE library? It's like no profound reason really. we might as well take an arithmetic scheme like BGB or CFS and try to get gates out of it. But TFHE already has a gate API. There's bootstrapping for every gate, and there's a default parameter set available. So we can theoretically just do all computations in FHE. Next. Rob, do you want to take this one?
Sure. This is the first time I've spoken at this presentation. So just I'm Rob, also from Google. Shruthi and I work together on this project. I am not a person on the cryptographic side of things. I am very much your basic engineer. I work with bits and I work with the conditionals and all these sort of things. So I was actually very excited to work on this project because we could take something from one domain that I have no experience with and convert it into a domain that I have a lot of experience with, being circuits and low-level software. So, you know, we are generally, all of us have written logic in the past, and we're familiar to your standard C-style for loop. Like if I want to iterate over something, I want to do some like sort of dot product-y thing here, I'm just going to write a loop, multiply a times b plus c, and add it to my accumulator, which is declared somewhere to this function. I just guess I left it out. But unfortunately, as you saw from the last slide, we don't have for loops or ints or all these handy operators. We've got and not. That's not helpful. But actually, you know, it brings us closer than we might think upon first glance. So when we have these fundamental logic gates like and or not, we know we hopefully are all familiar enough with basic digital logic, like these are building blocks of circuits. I can build an adder out of OR and XOR gates or AND gates, yeah, whatever. And then I can build a full adder out of that. I've got a bunch of adders, I can build a multiplier, so on and so forth. So we have the building blocks to build things that can express real logic. And those of us who took an algorithms class can remember, like, oh, you can represent any program as some sort of fixed circuit, assuming that, you know, the program has fixed input bounds, so on and so forth. So on one hand, we have NAND, which is functionally complete. You describe any Boolean logic in terms of NAND. And you have C, which is Turing complete, which is, you know, if you stand back and you kind of unfocus your eyes, there's a whole lot of overlap between the two concepts. The problem is, okay, C, Turing complete, great, I can describe circuits in it. Okay, so then what does the circuit that implements printf look like? The problem is there's so many abstraction layers built on abstraction layers built on abstraction layers that the code that we write in our usual environments isn't code that maps to a circuit cleanly. And the fact is, way underneath, what we're doing is we're clocking, you know, a CPU, which is, I mean, billions and billions of logic gates. So we need to think about this differently if we're going to generate circuits from programs. And that is where, just serendipitously, high-level synthesis came into the picture for this project. Now, high-level synthesis is a relatively, I won't say it's mature because there's still a lot of development going on there, but it is not a new methodology. General idea is writing Verilog and RTL, these low-level logical description languages. It's kind of painful. They're wonderful languages with a very rich history, but I've yet to meet the hardware engineer or, God forbid, software engineer that really likes touching it at all. It can be pretty gory pretty quick. So a couple smart folks have the smart idea of not using Verilog. The question is, then what do you use instead? A lot of techniques use familiar high-level languages such as C++. It's probably the most common one, actually. Catapult being one example. So then the idea is you describe a circuit, usually a combinational one, not a sequential one. Usually you want to describe just straight through logic in C++ or a subset thereof. You can imagine that you can't support arbitrary C++ like, say, standard tuple actually, well, standard algorithm is going to be a little difficult to lower. So then you take your high-level language and you lower it into Verilog. You don't try to go directly to a netlist, being a series, which is a series of logic gates describing the actual like implementation of the hardware. But this also must be cognizant of the limitations when you actually are designing a circuit. For example, your types are concrete. What does it mean to have a circuit that has a variable width interface? There are only so many bits wired into a block. You know, maybe not using them all the time, but there are only so many bits feeding into that block. Loops must be enrolled. Otherwise, your loop is no longer combinational. It needs to be clocked, which works. Of course, there are circuits that can clock multiple times, but it's, again, that's sequential, not combinational. And similarly, there's no real heap within a circuit. Of course, one could have implemented something like this, but boy, that's bizarre, and I don't know why you would ever do that. What a waste of resources. Answering Florence's question, because I see in the chat really quickly. There are no imminent plans, but kind of one of the upshots of this is that there's no reason why we couldn't. It's just a matter of, we'll see later, of putting a different front end in front of the middle and lower layers that we built up. It's really very, aside from the language, for a little overhead. So, Shruthi, is this where you pick up again? Where we talked about, wait a minute, FHE programming and hardware design. Again, you got to step back, you unfocus your eyes a little bit. They're not too dissimilar. They're sort of the same things with certain restrictions. Yeah, I'll let you go from here, Shruthi.
Exactly, they're kind of the same thing. So then we started off with Transpiler, and this is start off with this goal. On the left is basically a high-level program, C++, sum of two integers. On the right is an n-bit full adder. At this point, rewriting the program that worked on plain text to the program that works on ciphertext. A WE sample is basically the ciphertext data type here. The thing to note here is on top, the carry and temp, that we initialize some temporary variable, do some computation, and then delete the temporary variables. That's kind of the structuring of the code. And to go a little bit, to give a bit of like fast overview of what the transpiler is, it has few stages. Next, C++ from XLS, sorry, yeah, from C++ to what XLS IR is nothing but an intermediate representation. We use all the awesome tools by the hardware team, the XLS team, Rob's team, basically. XLScc converts C++ into an intermediate representation, which Rob will talk much more about later. And then there's an optimizer, which optimizes the intermediate representation for hardware. And the IR itself has some high-level ops like sum and multiply. So that's why we have the need to booleanize it to convert everything into and or not gates. And then once we have the entire program with just gates, we can just rewrite that into C++. So looking at a very basic example, here is an example of string capitalization, which capitalizes the first letter of every word in a string. The thing to note here is we've converted that loop, which goes through character, into a functional unit with state. The state here is whether the last character was a space. If the last character was a space, then the current character gets capitalized, otherwise it stays as is. So this program goes through XLScc and gets converted into XLS IR next, and that kind of looks like that. And then we run it through the optimizer, and that kind of looks like the next slide. And then we take this optimizer, which still has some add and select, and booleanize it, next slide, which has just and or not gates. And next we see a visualization of this booleanized IR. The tiny program kind of blows up into this huge graph. Next, and so at this point, basically we can you can see on the top are the inputs and the bottom are the outputs. It's just traversing this graph and kind of rewriting the red nodes, which are basically red or orange or pinkish color nodes. They're basically and or not gates into C++. Next. And so the code looks like this, and next it kind of sort of works. On the top left is a string where nothing is capitalized. On the right is the computation happening character by character. And on the bottom, if you see the highlighted thing, you can see that it in fact capitalized the first letter of every string. Hey, it works. But don't get super excited, because it's slow. FHE is slow, but there are some optimizations in there, and I'll let Rob walk you through more examples and cool stuff.
Sure, sure. First of all, don't hesitate to ping if I have connection issues. I've heard that I've dropped out some. I expected the bandwidth at Google to be more reliable than that in my house. We'll see. Anyways, so yeah, I'm going to walk us through a quick demo. You might wonder why I'm doing it so early. You'll understand by the time the demo is done. So let me switch into, oh no, I'm in the right client. So what I'm going to do is I'm going to build my example program. I'll build it first. We'll get to it later. I'm going to build Transpiler. Am I here? Okay. Basil, build.
Rob, you're still on the slides.
I need to share the right screen, don't I? Chrome tab. Thank you. So yes, okay. Can you see my terminal now?
Yeah,
thanks.
We're
thank
good.
you. Those templates, and what's the name of this one? It's going to be mole TFHE test bench. Perfect. Great. Okay, so while that builds, let's go look at the code that it's actually, let's let that build first, and then we'll go to code. Let's fire this up. So simple regular build program. I'm going to start this program running, and let's look at the code I'm building. Actually, I'll get to that later. First, I want to talk about the inner layers of this transpiler. So I'm going to switch back to the other tab now, Lord. Hopefully I'm switching the right window. Okay, great. So, right. So I am, as Shruthi said, on the XLS team at Google, which is a high-level synthesis team. I apologize for our acronym being accelerated hardware synthesis, but people on my team love that letter X. They also started the XLA team, for those of you familiar with TensorFlow. So in general, yeah, writing RTL is terrible. And C++ is great for software. I love it, but it is horrible for hardware. The fact is, to map C++ onto hardware, it's a lot like making CUDA code super general. You can do a lot of things that will ruin your program and make you tie yourself in knots over if you don't really understand the problem. Using C++ makes it really easy to not understand the problem that you're addressing. That fact you were trying to lower a computation onto a fixed circuit. Still, people use it anyway. There are very successful projects out there. Again, Catapult, I think Chisel's public as well that come to mind, that people use to great effect. But we think there's room for an alternative. So we provide like a domain-specific language, DSLX, again, because people love that letter, that really maps much better to hardware. It offers like high-level language utilities such as parameterization and higher-level operators. But it's still cognizant of differences between hardware and software. XLS is kind of a rich tool set. Again, we have our high-level language. We have hardware-specific intermediate representation. A lot of folks will immediately reflexively ask, why not use LLVM IR? And LLVM is fantastic. We make heavy use of it in our tool set to compile programs down to native code. But the problem is it's really not tuned towards hardware. What's a GEP? What's a GEP instruction? A get element pointer instruction as relates to hardware? It doesn't make sense. So using LLVM and other tools like this, you end up kind of trying to shove this square peg into this round hole, and the pain is usually worth more than the effort. Like these other tools, XLS lowers down to Verilog or system Verilog. But really the most important thing here, we have logical verification tools, let you prove like this circuit is equivalent logically to this circuit. Like no matter, is this transformation safe and semantics preserving? It's pretty neat stuff. But the most important part here is our IR tools. For those of you who are less familiar with compilers and such, no one ever works in terms of your input high-level language. If you're a compiler trying to read C, you are going to, you are going to convert that C into some representation that's a lot easier for the computer, the compiler writer, the optimization writer to understand. And the same thing for XLS, the same thing for any language. So the XLS IR is really our layer for manipulating circuits, transforming them, generally any modification we want to perform, either an optimization or, for example, some other sort of transformation that we'll get to shortly. So here on the right, we have the pipeline, the full pipeline for the transpiler. You can see we have this layer where we take input C++, lower it to XLS IR, we just spoke about, we optimize it, and then we booleanify it, which we'll talk about in a little bit, and then you're left with this transpiled C++. So XLScc, the entry level to the front end to this tool, is a C++ compiler, that's C++ front end. Now I know I just said that C++ front ends are dangerous to use the high level synthesis, and I would still maintain that they are for things that intend to lower to real circuits. Here though, it sort of makes sense, and as long as you're cognizant of the limitations, it's a great tool. It does make some modifications or has some differences than your standard C front end. For one thing, it's client-based, but it doesn't output XLS IR. It's kind of a big difference. The other is that, like, your standard if-else scheme is going to usually be lower to assembly or an IR. So it's going to be like, if condition 1, we proceed through one block, and if not, we jump to the next block. If condition 2, we jump to this one block, otherwise we'll jump to this other block, so on and so forth. For loops are the same way. That's not what hardware is. There are no jumps in a circuit. As Shruthi said before, like if you need to switch between conditions in a circuit, you have either what's called a selects or it's a mux. Same thing for loops. You can't have dynamic loops. They have to have static sizes and they need to be fully unrolled. Same thing for all data. All data must have fixed size and all computations must be a fixed length. Sounds draconian, but in practice, most problems that kind of are fixed scope, like calculate this value, do this transformation on a string, fit these pretty well. It's arbitrary things like handling user input from the internet. Just where things get a little fuzzier. But as a result, XLScc spits out the details needed to make a combinational circuit. The asterisk though implies like, oh, the circuit is composed of high-level ops that C++ would execute, like multiply, and these operations are going to be multi-bit. So like you might have a 32-bit multiply. There is no one cell you can buy from a vendor that will do a 32-bit multiply. We'll get to how we work around that later. So for example, we're going to talk about multiplies, and we're going to talk about 8 and 16-bit multiplies. So we have here on the left is some C function, C++ function to implement 8-bit multiply, return x times y, pretty straightforward. On the right is the corresponding XLS IR. It's a lot more verbose. IRs usually are. They carry a lot of metadata with them. For example, the ID and position tags here let us know how they correspond to lines in the original source. But otherwise, you can kind of look at this and see like, okay, I'm taking in x and y. They must be 8-bit wide vectors, 8-bit vectors. Returns an 8-bit quantity, and it does an unsigned multiply of x and y. Understandable enough. Before we move on from XLScc, we should talk about some of the limitations of it as a front end. XLScc and fully homomorphic, transpiled fully homomorphic programs are a new space. They're not just C++ that I moved somewhere else. They're a new space of computation. So you get exactly what you bring with. There is no C standard library or standard lib.h unless you bring it with you into that space, unless you compile your program with a version of it that is available to XLScc. This is an engineering challenge, not a foundational one, but right, and basically to say right now, the amount of supporting tools, amount of tool support is rather thin, but it will expand over time. There is kind of talking about how C++ isn't hardware. There's no conception of threads or thread local data, time, so on and so forth. And some advanced language features may or may not work. Standard function could work theoretically, assuming you defined a version that had like static data and a maximum size of it. A little fuzzy, wonder why I'd be using it, but like that's a language feature. It could work, but use at your own risk, at least in the short term. Keep it simple and you'll be much happier. So the next stage of the process is we optimize this IR. And we have a mixture of, you can use a mixture of either generic optimization passes or hardware specific ones. Generic ones being DCE, dead code elimination, DCE, common sub-expression elimination, basically duplicating, removing code where it could be, where it doesn't have to be duplicated or whatever. There's some op narrowing passes where you're doing a 32-bit multiply, but you only ever need the last 4 bits. Well, let's throw away the top 28 bits, so on and so forth. There's another set of optimizations I think are rather interesting that are BDD-based binary decision diagrams. These are canonical representations of binary trees. And once you can convert your program into this format, there's a lot of really, really neat stuff you can do with it. A little of it is scary and unfamiliar to me, but just basically there's a lot of domain-specific stuff we can do as well, are doing. For this program, though, it's for this, the mul 8 program we're showing, there's nothing to show for optimization. It's one cell. There's no optimization being made. Sorry about that, but I don't want the example to get too complex to walk through. The next bit is one that's near and dear to my heart. I love it. It's the booleanifier. So we saw before that TFHE's API was written in terms of and or not on single bit quantities. But we saw before that we have 8-bit multiplies. How do we connect those two worlds? High level, complex, low level gates. That's the booleanifier. There's a tool in XLS pre-existing called the abstract evaluator, which we basically defined to implement operations that cannot be expressed in a circuit in terms of lower level operations. Just like before, I showed how described how multipliers in terms of a full adder. Well, a full adder can be implemented in terms of a half adder. Half adder can be implemented in terms of and or not, and that's exactly what happens here. So basically, I adapted this scheme to lower itself all the way down to these gates all the time, and to break apart every operation. Oh, there's a 8-bit and 16-bit and. Well, okay, I need you to break that up into 16 full adders or 16 1-bit ands, so on and so forth. And in that way, we finally convert this high level, what started as the C++ mul, we converted into this IR mul, and now we've converted it into individual logic gates. The last step, oh, right, and here's what it looks like. So I picked multiply very specifically because multiplies sound easy in your head. I'm just gonna multiply 2 numbers, but they explode. They explode big. In fact, this code listing, this IR listing, is not even half of it. The full picture is this. Oh gosh, the gate space of simple operations expands very, very quickly. And keep in mind, this is only an 8-bit multiply. Imagine if you expand it to 32 bits. You know the space isn't increasing by 4-fold. It's increasing by some power of probably of 2. I don't know the exact scaling, but understand it's not going to be linear. This goes to show that writing this type of code directly to these FHE libraries, it's not going to fly. You can't describe any complicated language in these terms. What you need is some toolchain like this one to lower these complex operations into this form. It's also worth noting, we'll get to this later, how long does it take to evaluate a circuit? It's not like a program. You can't short circuit. You've got to evaluate, because you're using muxes to determine the final output of the program, you have to evaluate every cell or every gate in your network. So you can see how you start doing multiplies, things start getting slow real fast. That being said, the last step in our transpiler is to convert it back into these TFHE calls to create a C function that realizes our initial function, except in terms of these FHE gate operations. And given this XLS, up here, actually pretty easy to see. You take your AND gate, well, you convert that into a call to TFHE boots AND. You have an OR gate, boots OR, so on and so forth. The eagle-eyed amongst you may see a different sort of op, bit slice, and that has a pair called concat at the end of the function. When we call into these functions, they take 8-bit wide inputs and they expect an 8-bit wide output. In this case, of course, you can use arbitrary types, floats, doubles, uint32s, uint64s, so on and so forth. But the Boolean operations need a way of accessing the individual bits in the input quantities. And so what bit slice is it basically like, give me bit n out of this bit vector, give me bit y out of this other bit vector, and concat squishes them back in together so you have a single output element to pass out. So right, yeah, you take your XLS IR and map it onto these gates. You explode your inputs, individual bits, and you unexplode your outputs from individual bits into these composite units. As a result, you get code that looks like this. You can sort of see, hopefully, how this maps onto the XLS IR. It gives you this function, this mul8, named as you might expect. It takes in 2 samples, and it takes in a result pointer, 2 samples. And you can see how, like, okay, we're copying. This is basically the bit slice operation, and the boots and, boots or, boots not, those are your Boolean gates that we're referencing. So now let's circle back to the demo such as it is. Let me make sure this time I switch to the right tab. Great. So let's see how well things did. Oh, I ran that's cheating. Oh, that's pretty terrible. It took 6.5 minutes to multiply 2 16-bit numbers. That is tragic. Well, fortunately, if we're only doing 8-bit numbers, well, okay, it takes a quarter of the time. That's great. Let's say I've got a complex operation that I want to apply across a broad series of numbers. Well, C++ lets us do that. Consider this silly little example I wrote up, mul.h. Oh, let me embiggen this so you can actually see it. Right? Is that legible? I unfortunately cannot see my screen at the moment.
Yeah, that's good.
Great. Okay, thank you, thank you. So here I've written this stupid little function, slightly misnamed mul, multiplies the first 2 arguments and adds it to the 3rd one. But notice that it's templatized. Obviously, for this example, it doesn't matter. But say you had a very, very complicated program. You could then templatize it over your argument. And so your uint8 would be able to operate over very much smaller data sizes than your uint16. You change the template parameter, and boom, you've got a new function that operates only on the bit widths you need. I think hopefully from the results you saw of the computation, 6.5 minutes versus 1.5, you need to do this. You can't just assume that, oh, I'm going to throw an int everywhere and be happy with the performance. So let's see. So if we look, then we see, okay, so we've got mul.h and then mul8 and mul16. So if I look at mul8.cc, it's going to look like you expect. We're just instantiating this mul function with character data. In case you're unfamiliar with C++, we don't have to specify the type because it can be inferred from the fact that there was unsigned characters, uint8t's. Also, you might note, like, why are you using unsigned characters? That's because I don't have C standard int in this environment yet, so I have to use built-in types. But it's just a matter of writing the library and including it into the XLScc build flow. So I want to switch back to the presentation for a second. We'll come back to the demo again in a minute, but one thing at a time. So, right. So we saw that I used templates to avoid using just throwing int everywhere, because why would I care? And we've all learned that FHE cares very, very deeply. You should never let this go. So let's only use the types we need. Using high-level language features, templates are something that's really hard to reproduce on your own. So this shows that, like, oh yes, using C++ and using high-level languages is absolutely a good approach for this type of problem. But performance was pretty terrible. As proud as we are of this work, like, no one's gonna use it if it takes not almost 10 minutes, but more than 5 minutes to multiply 2 small numbers. So what can we do? Let's look back at the graph produced by the Booleanizer. What shape is it? Is it a straight line, so to speak? No. Well, if it was a straight line, what would that mean? That would mean that basically every output generated, every gate generated an output that was immediately used by subsequent gates, and those outputs would be immediately used by subsequent gates, immediately used. In other words, there was no opportunity for parallelism. Whereas this graph, it's very broad, it's very wide. I can't read this, but I can tell you just from a scanning that, like, oh, I see a gate here that doesn't use inputs from another gate. It's not a fully connected network, I guess is what I'm trying to say. So what can we do with this data? We know it's parallelizable, so let's parallelize it. And what some very clever folks did, actually Eric in the chat was one of them, I can't take credit for his idea, it's in Sean's idea, was to, instead of statically compiling the graph into directly into a series of TFHE calls, create an interpreter, a multi-threaded interpreter. And what this does, is it takes the graph we just saw, topologically sorts it. That means in an order where their nodes are sorted by the order in which they can be activated by previous nodes. There's a much better way to put it. But then it basically, you spawn a bunch of threads and they just pull things off the front of that sorted graph and execute it. And then they look at their outputs and like, okay, I produced these two outputs, which enables these other nodes to execute. And then other threads can pick those up and execute them, and so on and so forth until eventually you're done. This does sort of result in like a fork join type of model execution, whereas you're limiting your parallelism up front and you're limiting your parallelism down below. But it does actually yield tremendous improvements in practice. So there's another version of this program I wrote. Instead of just the TFHE test bench, it's the it's the interpreted TFHE test bench, interpreted TFHE test bench. And so we will fire this up. We'll save time. I'll cheat. I'll jump to the end. Instead of taking 6.5 minutes, it took less than a half minute. And if we're doing the 8-bit version, it took less than 10 seconds. Obviously, this is a huge improvement, closer to where we want to be. I mean, no one improvement is going to get FHE from being 6.5 minutes to multiply down to milliseconds, but I will take these tenfold improvements wherever I can get them, and eventually that's going to get us to the holy grail of real time, or as close as we're going to reasonably get within this lifetime. So that's in the demo stuff. Let's get back to the slides. So just a couple more features of the transpiler I wanted to talk about because they're perhaps particularly non-obvious or difficult. Arrays. A big feature for folks is that they wanted to be able to support arrays, particularly multi-dimensional arrays inside of the transpiler environment. And it wasn't immediately clear how to do that. But once we realized, like, okay, what's an int? It's just it's a series of 32 bits all packed next to each other. What's an array of 2 ints? Well, it's going to be a series of 32 and 64 bits packed next to each other. And so what's a multi-dimensional array? What's an array is just packed bits next to packed bits. And a multi-dimensional array is just packed bits next to packed bits next to packed bits, which is really hard to say. Oh my gosh. So you see on the graph on the right, this is sort of like what a int by 4 by 3 by 2, or I should have called it int, a 4 by 3 by 2 wide bit vector would look like laid out in memory and basically across the native fully homomorphic space boundary. You're just going to have element 0, 0, 1, and then you increment the middle dimension. It's basically counting. We all know how this works. And so really, this is an example of just like, oh, these types are composing. I'm starting with something basic. I can build something more advanced that wraps that, and something only slightly more advanced that wraps that, so on and so forth. And that's really how we came to implement structs as well too. What is a struct? Ignoring native type alignment and padding issues. Sometimes the compiler would throw in a alignment byte between elements of a struct. Ignoring that, what is a struct? It's just a bundle of bits stapled next to each other. So the structure on the right, which is A16.8, well, it would look like something below it, where the first 8 bits belong to element A, the next 16 belong to element B, and the last 8 belong to C. Easy peasy. The problem with this, though, is unlike arrays, accessing members of a struct and modifying them can be really, really painful in practice. Say I want to say I'm dealing with the C structure, the native layout, unencrypted plain text version of a structure, and I modify element B. Great, okay. Element.b equals foo. Done. Now say I want to move that to the the ciphertext version of that. How I encrypt this bit and then mask it into this other bitwise representation, it's horrible. So what we did is in the transpiler, we generated converters that will automatically handle this space transformation for you. You specify your ciphertext, it'll convert it into plain text. You specify your plain text, you modify bits on it, it'll convert it to ciphertext for you. It should make things much easier. And so, okay, I think we're coming up on the tail end of this. So now, really quick, what are forever limitations, kind of structural fundamental limitations of this approach that I don't believe are solvable without extreme methods, such as implementing your whole CPU within the TFHE space. First is execution time. there aren't tricks you can apply here. You're going to have to evaluate every gate in the circuit for each cycle every time you call a function in FHE space. There's no short circuiting because every mux has to be evaluated to see if it affects the output result. Dynamic loops. Dynamic loops cannot be supported by this scheme. And this unfortunately ties brains and knots a little bit because say I have some piece of data that needs to be iterated over 3 times to get a result. And Shruthi over there, her data needs 6 iterations to complete. Well, that difference in numbers, the difference of 3, that is a piece of side channel data, and that leaks out if we have to cycle them different times. So either we just run my data, cycle my data 6 times total, wasting 3 cycles, or we either do that or we just implement the circuit as an unrolled 6-way loop. You can't cheat in that way. You can't cheat with dynamic loops because that leaks side channel information. Finally, pointers. People really get hung up on pointers, but if you think about what they represent, they're either you don't want them, or it's they're either you can't have them, they're a total waste. Across the fully homomorphic host native space boundary, they don't make sense because the fully homomorphic space, when you're computing a fully homomorphic operation, that is a separate computing space. There is no, the address space starts from sort of nowhere. It is not, it's memory space. It's virtual machine basically is not yours. It is a different environment. You could use pointers. You could pass a heap type of structure in and out, this dynamically unclearly allocated space. But still, that's data you're passing into your computation. That is data that is part of your computation, which means it is occupying space in your graph, which means it's slowing you down. If you're computing something in fully homomorphic space, you must know its size and tailor your computation accordingly. Carrying around lots of extra, maybe I'll use this heap space, is just going to murder your performance. That you don't have to. Just tailor your operation. I mean, Lord forbid, you could JIT this stuff. You could come up with some operation that you don't know statically, come up with it dynamically, and then dynamically create and compile to native code your computation with it being tailored to the exact sizes you need. There are ways around this that don't involve pointers that are not going to murder your performance. So this is where we hand off. For the transpiler itself, our future work is the interpreter. Such a great idea, and there's so much more we can do with it. Right now, it's basically spin up 20 threads and have them just pick things up off the queue when you want. Anyone with experience in distributed systems knows you can do a lot better. You can have cooperative sharing schemes, you can have batching schemes, and heck, my desktop at work, getting a little old, only has 20 cores, but what if I wanted to use somebody else's machines or whole cluster machines? Say my graph was big enough that I could use 100 machines. That's going to do a whole lot to give us speed up. So already we can, for reasonable problems, kind of throw 100-fold speed up out there based on what we get natively just by adding the support for distributed computation. We haven't even started to investigate optimizations for this domain in particular. There are lots of, I'm sure there are lots of things we could do, but just zero bandwidth to do it so far. But I mean, any space has its own custom opportunities for optimization. We could explore those here. There's more we could possibly do with templatizing. Can't templatize across the fully homomorphic boundary because then what do you tell XLScc to do to instantiate these templates? You're kind of missing it. You're missing some feedback loop into the system somewhat. Oh, and finally, I forgot to put this on the slide. Right now, we are not targeting even the full set of operations that TFHE supports. It has a CMUX operator, which we're not using. We are lowering selections in muxes onto and OR gates, and so that's going to kill a lot of performance right there. Just a matter of finding the time. For a lot of us, this project is constructed out of volunteer labor, and as we get going more, there's going to be, I think, our throughput's only going to ramp up. But it's just, takes time to build the team. All right, Shruthi, I think it's all you from here.
Sure. So for our current transpiler, some of the immediate future steps that came up in the chat, questions in the chat as well. What more alternative backends can we add? Concrete, BGP, CKKS, whatnot? It's interesting that how much our optimizations that we got with interpreter for arithmetic ops, it would be much more for an FHE scheme that supports arithmetic ops by default. And being able to go back and forth between gate ops and arithmetic ops and kind of work the transpiler through to get the XLS IR to support and kind of find the right message space to ensure computation kind of goes through are all like immediate next directions. Something very interesting about the TFHE scheme is programmable bootstrapping and being able to take advantage of programmable bootstrapping, kind of figuring out which parts of the circuit form those univariate functions and can be taken as a block of bootstrap and then use programmable bootstrapping there. Like all of those are some good directions for our transpiler. Next, and if we talk about future directions for FHE transpilers and compilers in general, the power of transpilers here is that having that standardized API that FHE schemes can expose and having an independent IR, which is kind of sort of fully very expressible, and having high-level languages independent kind of helps us to make research progress in all the three different areas separately. Like coming up with more high-level languages like Java and Go and targeting the XLS IR or any IR for that matter can independently happen with the IR circuit optimizations to support arithmetic and programmable bootstrapping and whatnot. And independently, the FHE schemes can have their own like acceleration, both hardware and algorithmic optimizations. So compilers also make it easier to deploy FHE programs across different hardware.
Right, Shruthi, actually, I realize I should chime in here too. I forgot to note, just like the Transpiler project, XLS is also open source, so we can contribute across both projects totally openly and publicly. So a lot of these slot into both of our bread and butters. Just, I don't know, don't need to mention that. I forgot to.
Totally. I think TFHE, XLS, XLScc, all of the IR, all of those are open sourced, are all open source libraries. And future directions for FHE being practical in general, I think requires lots and lots of benchmarking. We are focused a lot on speed, but there's also cost of hardware. We could get the most fastest algorithm by avoiding bootstrapping altogether. But if the number of computations increase, then space also becomes, ciphertext expansion becomes a thing when we deploy things at scale. And ciphertext has to be transported from phone to server, then network bandwidth comes into place. So we need to pick security parameters that kind of help us make trade-offs for a specific application, trade-offs between all of these four: speed, space, and cost of hardware. And next slide. And I remember Pascal mentioning in the very first talk of the FHE.org series that FHE is where deep learning was 10 years ago, reaching the realm of feasibility, but doesn't have enough tools for widespread adoption. And transpilers are one of those tools. This is one of our inspirations that drove us to release this open source R transpiler. We'd love to see it move forward as a community effort. There's a community group for public discussion set up for this. Please play around in the repo, see what we currently have. Try to build your own demos. I've seen some cool demos come through. And reach out to us at the email above and let us know if you have use cases or ideas to take this to the next level. There are so many new steps. Looking forward to engaging with y'all in this space. Thanks.
Thank you very much, guys. This was super interesting. I think it echoes a lot of what we see in the community in general, that FHE now is less of a theoretical question, is really more of the practical question, is how do you bridge the gap so that any application developer can start using FHE? Because it's by having many people use it that eventually we'll learn how to make it better and better and better. So let's open up the floor for questions. Guys, feel free to just unmute yourself and ask questions directly.
mentioned kind of at the end, targeting other things, other schemes like BGP, BFE. Obviously, TFHE is amazing from the usability and sort of compilation standpoint because it doesn't really require things like noise management and ciphertext maintenance operations. Let's say things like relinearization, mod switching, those kind of operations. Would that be something that you would actually be able to express, let's say, in XLS IR, or would you have to modify or extend it somehow?
It's a good question. There would need to be, none of this should be quoted because I don't know. I suspect that you would have to have some type of side channel to like you take your IR alert to some level, and you probably have to have a side channel coming from above it, maybe XLScc or an intermediate layer that would kind of indicate, or some model basically saying these operations are going to, I don't know what the right term be, like create noise in the channel or I guess really what you need to do, I'd say it'd be a pass probably below the after XLSR was sort of done with the booleanization, that would probably basically model how the computation would evolve as it passed through the network, and then insert calls between, I guess probably just like add them on to a certain at the end of certain gates. I suspect this would be possible. I also suspect it would be a ton of work. But I mean, that's what they pay us for, I suppose. Yeah, no, that'd be actually a very interesting project because I think you get a lot of interesting like modeling work, particularly out of there. Yeah. Oh, Eric, you are muted, but I'm sure you have something very good to say.
Oh, sorry, go ahead.
Oh.
Okay, sorry, I wanted to add in that XLS IR is one, intermediate representations are many possible, and I think application specific and also like taking an IR and kind of like developing it to a point that supports specific application, but also having one that everything can target all applications is something that would be great to have, but we are kind of not there yet.
That is a good point. Unfortunately, that's a very good point. As much as I love XLS and XLS IR, it's possible. I'm not terribly familiar with the project, but it's possible something like an MLIR would build in the capability to carry around necessary metadata with you. But I still think, regardless, somewhere there has to be some modeling paths to understand how the computation evolves. And certainly don't, yeah. There are lots of things to work in.
They're definitely. Can I be heard now yet, or is it not working?
Yes.
Still?
Yes.
Okay, great. Then all I was going to say is just there already is a side channel we use to pass some information around the XLS IR and the transpiler. We call it the metadata system, and that could be used to move some of this stuff around. But yes, any library where you have to do your own noise management, where the library cannot track a noise bound as it goes, yeah, that's going to take some additional work. Something like an MLIR system might be necessary, or else we might be able to do some modeling as a second pass after the booleanifier using metadata passed from on high.
Cool. Thank you very much for the very detailed answer.
Oh, and thanks for the question. That's something I hadn't really considered before.
Just a quick question. Well, one, actually, I guess I have kind of two questions. But one is, so the parallelism that you're doing is seems to be like multiple instruction, multiple data. But I'm wondering if you had, if you were doing the same operations on, say, a whole array of data, could this be parallelized on a GPU or a TPU to speed it up?
That is a, I'm sorry. Yeah. That is, I lost the tail end of what you're saying. But I think I got the gist of it. Oh, hear me? There you go. Now I can, yeah.
Yeah, I was asking if you could speed computation on a GPU or TPU if you're operating on an array of data using the same operations.
Yeah, I will start, and Shruthi, you fill in anything at the very end. I can speak particularly to the GPU portion. We've looked at that, and I think that is absolutely worth a lot more investment. The libraries I'm familiar with seem to be more focused on the use as many resources to accelerate one gate instead of accelerate many gates. Yes, using SIMD basically formats. I think there is enough parallelism that a SIMD approach should yield really, really good benefits. I'm not aware of any SIMD machines except for GPUs that are commonly available. The age of the vector machine is sadly past. Yeah, I think that's something that should that deserves a lot more investigation. Shruthi, do you have anything to say TPU angle?
Yeah, I think in general, parallelization, there would definitely be some parallelization in GPUs or TPUs, and I think that would differ for different FHE schemes as well. Something to think about, not just TFHE, but as we look at arithmetic, I guess some schemes are more SIMD batching friendly, and that's also something that will be good to see. But yes, there would definitely be more parallelization and more speed up with more hardware.
Cool. The other question I had was, I guess, what are the pros and cons of sort of the transpilation strategy versus something more like say a NumPy or TensorFlow strategy where you have an abstraction in the programming language that you can do operations on and stuff?
I think some advantage is just that you don't need to know too much cryptographic. So when you say NumPy or sorry, what was the question? When you say NumPy interface, does that mean using NumPy to transpile again, or just like coding with a NumPy cryptographically?
More like, so the idea that it seems to me that you could, provide an abstraction of like a fully homomorphic number that you could add and subtract and stuff, and sort of the invariance would be, specified in the library instead of in the transpilation layer. So either way, you sort of, I imagine, still have to have some understanding of like what is allowed and what isn't allowed and stuff. But like, I imagine you could, have a wrapper around an 8-bit int and add it to another wrapper around an 8-bit int and get, an encrypted output 8-bit int.
That's actually a great question. I think it's, sorry, Rob, I'm going to finish and then take the end of this. I think it's largely developer experience. With the transpiler itself, we focused on general purpose programming and then kind of letting whatever the XLScc tool kind of lets you lower. So there's really not much you need to know versus take an existing program and then just transpile it versus having to learn that newer abstraction. It's just the developer experience that gives you that advantage. Rob, please add what I missed.
Yeah, sorry, I think my connection is going out. So if you can't hear me, just skip. Sorry, but what you're bringing up is really kind of one of these like eternal problems okay, good. With computing and acceleration in general. I don't know if y'all have much experience with CUDA, but it's one of those things like marketing has always been make it simpler, make it simpler, make it simpler. But the things you do to make it simpler destroy performance. So like they always have these schemes where like, oh, we'll manage memory for the user. We'll make it so we'll automatically transfer data between the host and the device, or you can throw conditionals in and you can branch and you can jump and you can loop. But all those things are terrible for performance. So like there's this line you have to straddle between making the developer experience good and making sure you respect the reason for the tool to exist in the first place. So I can write whatever C++ I want and have it run on a GPU. Or I can really just tailor the heck out of it and spend my time with the nuts and bolts and making sure my memory accesses are unaligned and staggered and just the right way, and that my data fits within one warp and so on and so forth. There are no conditionals. And really, I'm more sympathetic to the latter because I'm using a GPU for speed. And so if I'm writing code that's just going to have terrible performance, I shouldn't be doing it in the first place. So if I'm writing FHE code, I'm using it for security, and security has to be the first principle. And so it's probably going, if a problem is important enough for me to use FHE in the first place, it's probably important enough to tweak to. But that being said, the developer experience still has to be such that it's accessible for people to even learn in the first place. So this is the super, super long way to say, yeah, there's a tension there, and you really have to be able to satisfy both communities.
Ryan, actually, I think you should really attend next month's meetup because we're specifically going to be making a code demo of a homomorphic NumPy library for demonstrating recurrent neural networks homomorphically. But it's
Cool.
you know, it's a different approach from what we're talking about today. And I think, you know, this is really where we are with homomorphic encryption. You know, it's you can do general purpose programming and go down, you know, to the Boolean circuitry, or you can do more of like, you know, arithmetic, higher level functional programming, where, you know, if you know you're manipulating integers and so on and so forth, you can have some shortcuts. I think it's just a different approach, and the tools are a little bit different. But definitely do come next month because that's exactly what we're going to be talking about.
Cool. Thanks.
Any other question, guys? I don't know, how long do you have, Rob, Shruthi, for the meetup today?
Yeah,
Technically, I have this room booked for another hour and a half, so I can eat lunch whenever.
Okay, great. So let's take another question if anybody has one.
I guess if nobody else has a question, I might have another one. And that's a bit about like the related work, right? So there's a couple of different FHE compilers, but I think most of them tend to focus on the arithmetic side of things. So BFE, BGV, CKKS. But there are some that also target TFHE. So I think the most recent one I can remember is E3, encrypt everything everywhere. And I think they also target TFHE, at least in one of their modes. I think what they do is they have like basically a mapping for every kind of like multiplication is just this circuit, if I remember correctly. They don't do any sort of dynamic things. But yeah, it's still, I mean, it's still sort of a compiler that takes C++, C++ in that case, to TFHE. Have you done some benchmarking against that to compare like how much you get from the optimization stages that you have?
I haven't. Eric, is this something you did a while ago? Because like you said, like benchmarks are the only way you can really, they're the only proof you really have about anything. So yes, it's something we need to do if we haven't, but I don't remember if someone did during our earlier steps.
Sorry.
Shruthi, do you know?
So I definitely didn't do the E3, any E3 benchmarking, but I was under the impression that E3 was more of a library that you could invoke from your code rather than a thing that compiled your, rather than a language in which you could express, it didn't seem that it was genuinely taking C++. It seemed like you needed to use its data types. You couldn't define your own very easily without going through its entire system.
That's a fair assessment of E3, though I think that honestly, most FHE compilers you will find do not actually perform much compilation in the true sense, right? So there are some disadvantages to the library thing. For example, not getting a global view of the circuit. So there's a big disadvantage, but I think the most successful FHE compiler ever, I mean, no offense right now, is the EVA compiler, right? Which does some crazy speed up things that like just, you know, like it's hard to beat as an expert developer, right? Like it's really hard to beat. And that is technically also not a compiler. I mean, it does sort of output something, but again, the first stage is actually running a Python script at runtime to sort of get something out, right? So it's, I think there's very few compilers that literally take like a text file as an input and then pass that. So, but yeah, it would be really exciting to see some comparisons against E3 because, and it shouldn't be a hard target. I think from my own experience with E3, it wasn't super fast or anything. So it should actually be very good publicity for the Transpiler.
Of course, the only trouble we have there is that establishing that any comparison is apples to apples can be a bit tricky, given that not everyone is going through the same, for instance, intermediate representation, execution backend, which is one of the theoretical one of the theoretical advantages of a modular pipeline compiler, which I won't claim that we've published anything modular yet. After all, the only modularity we have is the split between the transpiler backend and the interpreter backend. But there's always some future work that could be done targeting other libraries for them. Certainly for easy one-to-one comparison, other libraries that also export and not primitives.
So this talk was recorded. We're gonna publish it on FHE.org after we edit it a little bit. So I would like to thank everyone for coming today. We're trying to do those meetups on a monthly basis. So next one is probably, sorry, Rob, let me mute you. So next one is actually going to be probably at the end of September. So as I mentioned earlier, this is actually going to be taken by people in our team at Zama to show two things mostly. The first one is the new release of the Concrete framework, where we are actually releasing a lot of new features that were only in the TFHE library originally that we now have in Concrete. And we're also going to be making a demo of a homomorphic NumPy, I don't know if you can call it compiler, I'll say a homomorphic NumPy library. So guys, please sign up for next month. We're going to publish that very soon. Thank you again. Maybe I'd just like to make one comment. I think, one of the difficulty when it comes to FHE is that we're thinking about it from the traditional computer science perspective, so it's basically a program running on a CPU. I think that one of the things we found out working on this for a couple of years at Zama is there is actually probably never a way to match performances of non-encrypted computation if you're going to stick to a CPU. Just by virtue of, encrypting, you're effectively inflating the data. So you have more computation to do no matter what you do. So I think that there is going to be a very, very strong push for hardware acceleration going forward, and effectively having perhaps even more dedicated, FHE chips that will make it closer to real time, even if bootstrapping is still on a CPU itself. So, so I think that's definitely going to be a very exciting thing going forward. This kind of like, FHE acceleration space, and looking forward to have maybe some speakers also on the hardware acceleration side of things in the future at this meetup. Great. Thank you very much, everyone. And we will see you next month.